So I will be talking about the neural language models, about the past successes and the challenges as I do see them, like what can we do next to get some improvement. I also like think about this topic about the representation of language in the brains and machines. So in the beginning, I will talk about that, or like some ideas. So probably people did see something of this sort a little bit before, like some representations of the language as you get it from like some simple neural networks. Like this is the old example from Word2Vec where we are showing that the distributed representations of words, where we actually see the concepts has some vectors in high-dimensional spaces, have some interesting properties, and we can believe that possibly in our brains we have some similar representations when it comes to concepts, because it comes very naturally, but it's like a very shallow level of understanding of the language. So we can be thinking of like further, like how is actually the language represented in the machines and in the brains. In the machines, it's usually some mathematical models, and in the brains, like from my naive point of view, because I did read quickly when I was younger some neuroscience science articles about how intelligence works and how brains do work, and in my opinion, it's like super difficult question to answer, like how is the language represented in the brains. Like there's tons of possibilities. One can even wonder, like is the brain enough to study to understand how we humans process languages? What about, for example, our genes, like DNA and so on? Like we are certainly born with some prior knowledge that helps us, for example, to recognize faces much faster than we can learn in our lifetime. But also our ability to acquire language seems to be something that we are kind of like born with. So in my opinion, it's like all like complicated and like interconnected. So maybe actually it would be easier, instead of like thinking about the representation of the language in the brain to just and the machine. Maybe you can just think of comparing the abilities of the machine to solve kind of similar tasks as human can. And if the machine can actually solve all the tasks using language that an intelligent human can, then we can just say that there must be some correlation between the representations that the machine did have to develop and the representation that we have in the brain. So from my point of view, I'm more like interested in like this functional similarity, which still like is an open question, as I will get to it later. So back to like my point of view, like on the history of the neural language models, because I was working on it for many years as a student. In my opinion, the main obstacle to actually advance the language modeling field forward from the Engram models to neural networks, it was about the algorithms, and not just that, like it was necessary to open source the code so that different groups that didn't have like years of experience could work with these models efficiently. I think that one of the very underestimated factors that contributed to the success of neural language models was actually the well-tuned hyperparameters, because that's years of boring work that some people like me had to do, and then I think it's kind of overlooked when it comes to more like fashionable ideas. I think that one slightly overhyped factor is the computational power. It was certainly necessary for practical applications, but to just give an example, like when, for example, I was working on language modeling on datasets like Tree Bank, like it wasn't actually that large, and I've heard from a number of people that the reason why my experiment succeeded at the time was because the computers finally became fast enough. Well, that's actually not the case. Like if you would take, for example, the RNN-LM code that I did open source like more than 10 years ago, then it will actually run even like on the computers from the 90s. So I think that the explanation that we have to focus on increasing the computational power and all the money should be put into hardware and GPUs and TPUs, and that's actually what's driving the progress. In my opinion, that's not true. Like in my opinion, the core of the progress when it comes to research is really like about algorithms, about the ideas, and that's the driving force. The computational power enables us to use bigger models in practical situations. For applications, it's certainly necessary in many cases, like machine translation, to give an example, would not be practical if we would not have these speed ups using efficient hardware. But still, from my point of view, I think that we should be, as the researchers, we should be mainly thinking about developing new algorithms and new approaches, because that's the core of the progress. Here are just a few examples about like how difficult was it actually to make language modeling to work. That's like from one of my favorite language modeling researchers, Joshua Goodman, who did publish this like very interesting technical report in 2001, where he actually did show quite pessimistic message about advanced language modeling techniques. He basically tried all possible combinations of everything with everything. And what did he come actually with, if you look at the graph, is that if you are increasing the training size, then the gains that you get over some basic baseline, which was in this case like some trigram at good Turing smoothing, the gains are actually diminishing. So the more data you use, the smaller improvements you get from complex language modeling techniques at the time. And there was actually something that I had to fight with for quite a few years, that there was so much skepticism in the research community that if you have a huge amounts of data, then you don't have to do anything else than the n-grams. It was very tough to convince people that this is not the case. There's still some sign of hope, and that we can develop techniques that will work better on large data sets. Like today, I think it's well known already that neural networks, even if you train them on like half of the internet, that they will be working much better than the n-grams. But back in the days, just 10 years ago, majority of the research community was just convinced by these experiments that there is no hope. Actually, it convinced myself, like in this experiment where I was just tuning the performance of the models while increasing amount of training data. So you can see that the blue curve is the n-gram model, and the red curve is the neural network. And as we are increasing the amount of training data, which is on the x-axis, then actually the neural network is getting better faster than the n-gram. So I was very excited about this graph. It looks very simple. It's not fancy at all, but it's basically showing that it's the opposite of Joshua Goodman's conclusion. Basically here you can see that the more data you use, the bigger improvement there is coming from the neural network. One of the things that we had to do was to actually increase the hidden size of the neural network, as well as we were increasing the amount of the data, which today sounds obvious, but again, like back in the days, there were people who did think that 100 neurons should be enough for like any amount of training data because of the exponential number of combinations that you can make. Actually, that's what Joshua Benji was claiming back then. So it was certainly not an easy path towards this revolution in the language modeling. And here is just a graph showing what the neural networks did on the Pentry bank when it comes to perplexity. So you can see actually there was quite some plateau, like since the year 2000, there were like some diminishing gains because people are just combining n-gram with cache models and some models that did cluster boards together and just reinventing the same things again and again. So there wasn't that much, but with neural networks, there was this sudden jump in perplexity that got reduced almost by 50%, like just a couple of years, and that was this revolution with neural networks. So I think that nowadays this sounds simple, sure, everybody already knows that neural networks are good, but the core idea, in my opinion, in the neural networks is still kind of like the distributed representations. The graph that I was showing at the first slide, it does show it for the individual words, and the clustering of the words, as you could see, that's what the neural networks are really good at, and the language models are actually good at clustering even whole histories, and that's the reason why they work so well. But that's certainly not enough to get to something like intelligent language models. We still are far away from human level performance, and we can be wondering what is actually the missing component. What should we do as researchers? What should we focus on so that we would actually obtain, again, like some breakthrough in the future that would get us closer to this intelligence. Well, there's actually a lot of people who just think of the simplest thing to do at the moment, which is to just inflate the size of the models and use more data. And there's this hope that if you really just keep doing this for long enough, that you may actually obtain something like model that will mimic the intelligence. I don't think so, actually, and I will give some examples later, but I don't think so. But I think that a lot of people have this opinion at the moment. Well, it's also like a question: how would we measure the performance of the models? Typically, the perplexity is like pretty good metric, but it can get difficult once you train your model on everything that you can find, because there can be overlap between the test data and training data, and you can get, even nowadays, actually the biggest neural language models. I'm quite sure that they would be quite competitive compared to humans when it comes to perplexity, but some high-level understanding is still missing there, and not just that, even like simpler things. So here I just have some example that I did find on the web, because there's so much PR like nowadays about these huge language models, like from OpenAI, this GPT-3, which I think is the latest one, where you just show the language model some text in the beginning, and then you just continue generating the rest by just sampling from the language model, from its probability distribution, and it certainly looks very cool, and you can get some funny examples. And here we have basically conversation between Shannon and Turing about Turing's paper, and if you actually read it, sort of makes sense and looks really cool. Well, it also makes it harder to understand what this model actually would be failing at, like why I would not consider it still intelligent. I think that we are making somewhat like a mistake when we look at these models, kind of like looking into the mirror and believing that the image is alive, because these models are like their power comes from the huge amount of data, and they are just reproducing what some other humans did write, because they are trained on so much data. Like to put it into like a trivial example, if you would code a computer program that just outputs a sentence, "I am an intelligent computer," then, well, like pretty much no one would see this as a valid example of intelligent machine, because you would just say, "Oh, this is trivial," like the computer just said. But the human programmer that did type, and the intelligence here is not on the side of the program; it's on the side of the programmer who did actually code this program. There's no interestingness in this computer program. It's static; it cannot say anything else. There's nothing interesting about it. But it's actually quite similar when it comes to language models. It's more complex to see it, because if you train the language model on huge amounts of data, it can repeat text from many books. Then again, like looking into the mirror, you can believe for some time that there's some intelligence in there. But the intelligence, again, is hidden in the data that the model was trained on, and the data was produced by humans, not by the machines. So I think that the justice is hard to sometimes understand for people who do see these examples of generated text, and sometimes they get the impression that we really are getting close to some AGI or whatever, which in my opinion is certainly not the case. So what is actually missing? Like from my point of view, there are like many things that we can talk about, and they are quite related. So I would say that we should probably have models that can learn without the hard supervision, like that do not need to mimic some training data, but models that can do something interesting without just having stochastic gradient descent by propagating errors from some training examples, because that doesn't seem to be the principle that we are based on, like people. We don't learn language from some hard supervision. Certainly we can produce new sentences, we are creative, we can do new things. Also, like the language models today, like still struggle with the memory. We have like some good models for short-term memory, like all kinds of recurrent architectures, so like these transformers. But when it comes to longer memory, if you would just look at these generated texts, you would quickly find that it's more like some inconsistent dream that these models can keep generating text about some topic, then switch to some other topic, and it's basically inconsistent. And the model, after a while, forgets what it generated like a couple of hundred words ago, and again, it's inconsistent, and we don't really have a good mathematical model that can support long-term memory. It's actually quite easy to say that, but I think the memory itself is quite close to intelligence, because memory is not just like the human memory is not just some raw copy of the sensory information, but we do remember things based on our intelligence as well. Just think of how is it if you go, for example, for holiday somewhere to a country where people speak the language to understand, or if they speak a language that you don't understand, you will remember much more if you actually understand other people than if you just process some signals that are incomprehensible for you. So the memory is certainly more complex than just a copy. Further, I think that we can, as humans, like this human level language understanding allows us to create some new stories. We can write whole books, we can increase in complexity, we can add words to our vocabulary, we can add ideas. That's again something that these models, like you can have this huge GPT-3 model, and it's still the same language model as like 10 years ago. It's just after the training phase stops and all the parameters are frozen, and it never actually learns anything. It will just stay at the same place forever. Even if you keep generating text from it from millions of years, it will never get out of its original distribution. So there's this interesting idea of thinking of language as a complex system, where actually complex systems are like some systems that are composed out of simple units, where we just apply some function on these units iteratively again and again, and then you have emerging patterns that you can observe that are not obviously present in the original starting state of the system. It's not also like visible in this function that you apply to the complex systems, but somehow this complexity emerges. You can think of even like not just language being a complex system, the whole universe can be seen as a complex system, or life, DNA, all these things. Evolution can be considered a complex system. Well, again, like you can think of the whole universe as being something that is in principle something simple, but by applying the rules of physics iteratively, you just get through evolution all these structures that we can see around ourselves. And I think that's actually quite an interesting topic. If we can actually come up with mathematical models that would allow this complexity growth, unlike traditional neural networks that just are basically having fixed complexity. And if we can actually build some language models around these ideas, so that's something that I would consider like an exciting research direction, like where we can develop systems that can become more complex through the evolutionary mechanisms, just like the complex systems. Here's just some idea. It's actually not that easy to compare like different systems, what is more complex, what is less complex. It's kind of intuitively like I'd say obvious to us that we would say that the picture on the left is too regular. It's not very complex because we can describe it very, very easily. The picture in the middle is maybe more complex, but it's still quite regular, and the fractal on the right is much more complex. Well, if you would consider, for example, Kolmogorov complexity, or like in other words, minimum description length, then in all these cases, all these patterns can be generated from very, very short programs with fixed length. So all of them would be actually having quite low complexity, which is kind of like counterintuitive. So it's actually not that easy to come up with good metrics of complexity. We actually tried to do something like that together with my students here at CIIRC in Prague. So like motivational example that I think probably most of you know is the game of life, which was manually designed to generate some kind of like complex or emerging patterns. And we were thinking whether we can actually like design automatically some 2D solar automata, because game of life is a solar automaton, whether we can automatically design automata that will be just like game of life, able to exhibit some sort of like a emergence of structures. How would it look like? So we did actually sample a lot of random 2D solar automata, and then we try to pick ones where actually the structures appear and at the same time are somewhat stable over time, because if it would just be sampling the ones where actually new structures appear, then the most complex then would be kind of like the chaotic automata, which look like white noise, but that's actually again like not intuitively complex to us. So we wanted also like to have the stability of the patterns over time, that new patterns should emerge, but they should be present in the future steps. And this is like a few examples that we did find a couple of years ago. It's like in this paper called Evolving Structures in Complex Systems, if you want to see the details. But basically, we could observe for a lot of different systems that where actually some sort of like complexity growth did appear to be happening, like all kind of like glider structures that are propagating over the space. There was also like a other project where it was more like based on more like mathematically oriented approach to find complex systems. And in this case, it was based on the idea that there are transients, which is basically the number of time steps that it takes before the complex system enters a loop, before it basically starts to repeat itself there. And if you have a very small one, then actually it's guaranteed that it has to actually start looping at some point. So you can actually measure how quickly the transients increase as you are increasing the size of the automaton. And we did find that if they don't increase at all, then that was the case for all these stable automata that are doing kind of like nothing, and they just die out. For example, the activations in them, if the transients were growing exponentially fast, then it was the case of the chaotic automata, where we just don't really have any observable patterns. And here these examples are for the like class where the transients are growing polynomially quickly with increasing size of the automaton. And that's actually again like this interesting class for us, where there seems to be some kind of like a complexity growth, and you can see that there was a lot of like diverse behaviors that we could find automatically. Well, now you can be wondering how this is related to these language models that I was talking about originally, right? Well, actually, that's what I wanted to basically show, that there are systems where actually new structures can unsupervisedly develop over time through like evolution, as it is happening here. And if we can develop, say, for example, language models that would be based around models that can increase in complexity, then there would be a chance for them to develop, for example, memory, or like create some new entries that the system can actually operate with in the future. And I think that that can be like a way how to move forward towards more like more intelligent language models that don't just rely on stochastic gradient distance for learning, and models that keep changing and evolving even in the test phase. And in fact, if you actually still want to see some neural networks here, then the solar automaton, you can actually see it as a recurrent convolutional network, which basically just like how people who just want to see neural networks everywhere would see these automata. So to conclude the talk, I think that to make some advancements in language modeling, it's not gonna be enough to just scale the amount of training data and size of the models, which certainly can produce very useful language models. And I think that models like GPT-3 are like even further, because it's likely that people will train even bigger models soon. They can be actually very useful. They can be they can allow development of new applications where, for example, people can do some grammar checking or like change of style of the text, or even generate some summaries of news articles, or even maybe generate text that will be personalized for concrete people. So I think that there can be tons of practical applications of what we already have. We don't actually need to do new research to obtain new useful applications for sure. But if we actually want to have intelligent language models, and if we want to make a further step towards having machines that represent and use language closer to how people do it, then we, in my opinion, should be actually thinking about like these big issues that the current technology has, about the limitations that the models do have. And if we have neural language models that actually don't change their parameters at all once they are trained, then I think that that's just not the same as the models that we have in our brains. We can certainly like acquire new knowledge by just talking with people, acquire new memory structures, create new memories, and build on top of what you've learned before. So all these topics like compositionality, memory, and so on, I think it's more like emergent property of a complex system. And if we are to succeed in developing language models that have these abilities, then I think that we should have first mathematical models that actually can increase in complexity and are based around these ideas that I described. So that's like my vision for the longer term future of the language modeling. Thanks for the attention, and we can go for the questions part.